All right. Worry about this lab crap in a bit. I would like to look at some more steady state sinusoidal circuit analysis problems. So let me let's see, don't need that. Don't need that. Save my transistor. Share the screen. All righty. So we're going to spend that's my wife. She should know that I'm in class. All right. So today we're going to do some more problems involving steady state sinusoidal circuit analysis. I'm trying to decide if we are going to bother with doing any problems that will actually require the use of nodal and mesh. The reason why I say bother with it is because we can't do that on our exams, and nodal and mesh are probably the circuit analysis techniques that most of you are the most familiar with. So it seems almost like a waste of time. Maybe not entirely, but probably of less benefit than looking at other ways to do things. So let's look at the following problem. If Vs of t is 5 cosine 100t volts, our goal is to figure out what our inductor current IL of t is. So how would we start approaching this problem? So let me ask you a question. Do you want to work this problem in the time domain or the frequency domain? Frequency domain. So our first step should be converting this circuit into the frequency domain 100% of the time. Okay, there's no ifs, ands, or buts about that. So how do I convert this circuit into the frequency domain? Fantastic question. Who can tell me what the frequency is? 100, okay? Why?
Omega t.
Right. So this voltage is of the form Vm cosine omega t plus some particular phase angle, which in this case, let me write that as theta v. Excuse me. Omega is our frequency of interest. So we do know what omega is. It is 100 radians per second. So how can I use that information? Okay. All right. Uh, 0.3 times 10 to the minus 3 henries, where a henry is a volt second per amp. And that's just going to give us units of ohms. Somebody do the math on that real quick. All right, so 0.03. Goodness gracious. All righty, so we have J 0.03 ohms here. What happens to the resistor? Stays the same. The impedance of the resistor is simply the resistor value itself. What do I do to my voltage source? So I have a time domain voltage and I'm trying to work in the frequency domain. What do I do? All of my voltages and currents should be replaced with phasors. What is the phasor representation of that voltage? So I agree that there's going to be a 5. What's next? All right, 5 with a phase angle of 0 degrees volts. This is going to be replaced with a phasor current IL, which means this guy is now going to be 1 or 0.2 multiplied by the phasor current IL. Okay. What do I do now? So is my circuit fully converted into the frequency domain? Let's start there. Are there any time domain quantities left? No. All right. So I have successfully completed step 1. Convert my circuit from the time domain to the frequency domain. All right. Now we can apply DC circuit analysis techniques. I believe you had suggested using nodal analysis. Okay. I both agree and disagree with your statement. Here's why I disagree with it. Nodal analysis implies that we're going to set up multiple Kirchhoff's current law equations here. And if we set up a system of equations, again, I cannot emphasize this enough, your calculator literally cannot do them with complex numbers in them. So we are avoiding systems of equations like they are the plague, okay? Yes, KCl is more in tune with what we could do. So if we did Kirchhoff's current law at this top middle node, where let's call this unknown voltage Vx. Goodness. We could come up with a single equation with that single unknown voltage Vx, which would allow us to solve for the current flowing through the inductor using Ohm's law in one more step. So how am I going to write that Kcl equation? How do I write any Kcl equation? All righty. So was that plus or minus 0.2 IL? Minus, okay. All right, what's next? Plus IL, that works. And set this equal to 0. This equation has two unknowns, so we're going to have to determine one other equation in which to substitute into here. Anybody have any ideas what that might be? All right, so using Ohm's law, IL, is equal to Vx divided by J 0.03 ohms, and we can substitute that in to here and here. So that means we're going to have Vx over 100 ohms. I'm going to put my equal sign way over here. When I move that 5, I'm effectively splitting Vx minus 5 angle 0 over 100 into two fractions, both having that common denominator of 100 ohms. And then I'm moving that constant value term to the right-hand side of the equal sign. So that's going to give me positive 5 angle 0 degrees volts divided by 100 ohms over there. So I've taken care of this guy and this guy. Negative 0.2 IL plus IL is just 0.8 IL. Everybody okay with that? And so now I'll have Vx divided by J 0.03 ohms. And so I can say that Vx, let's do this in two steps so I don't confuse anybody. 1 over 100 plus 0.8 over J 0.03 is equal to 5 angle 0 divided by 100. So what's 5 over 100? .05, right? From this, Vx is 0.05 angle 0 degrees amps divided by 1 over 100 plus 0.8 over J 0.03. And now we have something we can put in our calculator. Because if I am not mistaken, the TI calculators, at the least, cannot even do a simple numerical solve function. So one equation, one unknown with complex numbers in it. So I had to do algebra to get my unknown voltage Vx isolated. So I have 0.05 angle 0 divided by 1 over 100 plus 0.8 over 0.03 I. Whatever floats your boat. All right. Anybody get these answers? So I have 1.875 angle, very, very close to 90 degrees millivolts in polar form, or 0.703 microvolts plus J 1.875 millivolts. So when our angle is this close to 90, it should make sense that the real part should be very, 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 very small. All right, anybody else other than Carrot get it? All right, got a couple of more thumbs up. So I'll assume that I am correct. Let's see, what's the chat saying? Can I do a source transformation? Let me look at this guy real quick. I can scroll up. Yes, I could have done a source transformation. That would have put a 50 milliamp source in parallel with that 100 ohm resistor, in parallel with the dependent current source, in parallel with the inductor. From that step, I guess technically, I could do current division, but it might be a little hinky because I have that dependent source in there as well contributing current. So I feel like I would have wound up effectively doing source transformation and then winding up doing Kirchhoff's current law at the top node anyway. So that would have just added one more step. All right, so I have a tickle in the back of my throat that is making it difficult for me to breathe. Excuse me. All right. How do I find IL? Well, we have an equation for it right up here. So we simply take our voltage Vx, 1.875 angle 89.979 degrees millivolts, and we divide it by the impedance of our inductor. So divide that by 0.03 I. And we find that our inductor current is approximately 62.5 with an angle of negative 0.021 degrees milliamps, or 62.499 minus J 0.023 milliamps in rectangular form. All right, so I felt that that problem was fairly straightforward. That's an in-class assignment problem. I'll leave that to you guys. I'm trying to find something else that we can do. That won't involve setting up a system of equations. No, that would be a delta y transformation. You guys don't know how to do that yet. All right. I found one I think we can do. So this will be IS of t, this will be VS of t. Let's say that IS of t is 25 sine 10 to the 3 amps, and VS of t is 15 cosine 10 to the 3t volts, excuse me. So this is another, let's see, the quantity that I'm trying to find. This voltage, which we'll call V1. So I think we can do this without coming up with a system of equations. We shall very shortly find out. Excuse me. So what do I need to do first? Convert the circuit, absolutely. Alrighty, so let's look at our current source. What is the phasor representation of that current going to be? The current source. So 25 phase angle 0 or 25 phase angle minus 90?
I agree with that, minus 90.
Minus 90 because it's a sine function and we need to convert it to a cosine function. So 25 angle minus 90 degrees amps goes here. Somebody else tell me what's going on with my voltage source. What's its frequency domain representation? Kendra, I'm gonna pick on you because you're in front of me. All right, so to convert from the time domain to the frequency domain, we carry, again, two pieces of information, our magnitude and our phase angle. What's the magnitude? All right. What's our phase angle? Yes. There we go. All right, what do we do with our resistors? Stay the same. What about our capacitor? Yes, 1 over j omega c, which is the same as negative j divided by omega c. So that would be negative j divided by omega, which is 10 to the 3 radians per second, times our capacitor value, which is 1 times 10 to the minus 3. Let's see, a farad is an amp second per volt. So the second cancels out the per second. We have 1 over amps per volt, which is going to give us units of ohms. So negative j divided by 1 is simply negative j1 ohms, I believe. For our inductor, the equation did not change from the last problem. J omega L, omega 10 to the 3. L is 2 millihenries. And so this should give us positive J2 ohms. All right. So our goal here is to attempt to work this problem without employing nodal or mesh analysis. So what can I do? Yeah, I literally just said not using nodal and mesh.
I immediately regretted what I said.
All right, let's see what happens if we do superposition, right? There's no impedances that we can make. There is no, so there's no impedance combinations or anything like that that we could make that would ease our circuit analysis. So I'm going to go with superposition. And let's start with the voltage source on and the current source off. Let's call this guy V1 prime. Again, I haven't worked this problem out ahead of time, so I may regret saying we're going to try to work it without using nodal or mesh analysis, but I just want to see what we can do. So all of my impedances are going to stay the same. What's going to happen if we're working this voltage source on, current source off? What's going to happen to our current source? Open circuit. So our voltage source is going to stay on. All right. So this is the circuit that we are interested in, and we are trying to find that voltage V1 prime. And I firmly believe that we can do this without employing nodal analysis or mesh analysis. The question is, do you guys recognize how we can solve for it using not nodal analysis and not mesh analysis? So can we just do Ohm's law? So to find the voltage V1 prime using Ohm's law would mean that we would need to know the amount of current flowing through that 1 ohm resistor. Do we know that? No. So I would argue that we would either need to find that current first, or Ohm's law may not be the right methodology to employ here. Let me ask you guys a slightly different question. This is how I like to guide your way of thinking. Does the voltage that I've just labeled also represent that voltage V1 prime? Yes or no? Yes, okay. So I'm going to draw a little circuit here. I'm going to erase it momentarily. How would we approach determining the voltage Vx in a problem like this? How could we do it? Voltage division. How is what I've drawn here any different than what we have up here, except for the fact that there is impedances as opposed to just resistances? We have a voltage source in series with this impedance over here, in series with the parallel combination of impedances. It's literally the same circuit. May not look like it right off the bat, but it is exactly the same thing. So I'm going to employ voltage division. So using voltage division, I'm going to have V1 prime is equal to 15 angle 0 degrees volts what should be in my denominator, or excuse me, in my numerator?
Numerator. We're looking for the VI or we're looking for it in the yeah.
So 1 over the value is current division. Yeah, so we want the impedance that we're trying to find the voltage drop over, which would be the parallel combination of this 1 ohm resistor and this 1 ohm resistor in series with our capacitor. Correct? Is that the voltage? Is that the impedance that we're trying to find the voltage drop over? Yes, right? Okay. So I'm going to have 1 ohms multiplied by 1 minus J1 ohms. So the 1 ohms represents the topmost branch. The 1 minus J1 ohms represents that middle branch containing the resistor in series with the capacitor, divided by 1 ohms plus 1 minus j 1 ohms. So that's my numerator. What goes in my denominator? Exactly right. So the total series resistance seen by the source, which is exactly what that gentleman suggested. What we have in the numerator plus the other impedance, the J2 ohms, which is in series. So this will be 1 ohms times 1 minus J1 ohms over 1 plus 1 minus J1 plus J2. Now, one other thing to consider is that whenever we traditionally do voltage division, so we have our source voltage here. Let's just say we have 2 impedances in series because that's what we're treating this thing as. If we wanted, let's call this guy R1 and R2, the voltage drop VR1 would be defined with a positive polarity terminal connected to the positive polarity terminal of the source, and VR2 would have the same polarity as VR1. We are trying to find the voltage with the opposite polarity because the negative polarity terminal is connected to the positive polarity terminal of our source. So what do I need to do to modify my equation? Let me put it to you a slightly different way. Our source is the only thing that's supplying power in the system. Can we agree on that? So I would argue that the current that is leaving the source will be going out of the positive polarity terminal. Do I have anybody who disagrees with that statement? That current is then going to split up. Some of it's going to flow through this branch. Some of it's going to flow through this branch. And it's all going to recombine and flow down this way, right? We're treating those top 2 branches as a single impedance in parallel. So I would argue that that current's going to flow in this direction. Does the current see the negative polarity terminal or the positive polarity terminal first? So what do we do when we see the negative polarity terminal first? We put a negative sign. There we go. So that voltage will be negative by definition because our current that's leaving our source is flowing into the negative polarity terminal. Okay. Nothing different than what we did on all of the other instances of voltage division where we had the polarities of the voltage drop the wrong direction. All right, so let's take a moment, put this big clunky thing into our calculator. Can anybody verify that I've gotten the correct answer? All right, I'm seeing some heads nodding yes. Okay, so we have found the contribution of the 15 angle 0 volt source to the quantity V1 prime. What should we do next since we're employing the superposition technique here? Turn on the current source. Great. So with our current source on, this is where I'm not 100% sure that things are going to work out, but we'll give it a go. Ohms plus V1 double prime minus J1 J2. So if our current source is on, it's going to be in here. And it was 25 angle minus 90 degrees, if I'm not mistaken. What's going to happen with our voltage source? Short circuit. All right, so let's see if my decision to do this problem is going to bite me in the butt. It looks like the answer is yes. So what I mean by that is I'm still in a position where I have no means by which to combine any of my impedances or anything like that. I can't do any source transformations because I don't have a practical current source here. There is the current source, the ideal current source is not in parallel with anything. So as a method of last resort, we would have to do either nodal analysis or mesh analysis here, right? So with that in mind, we literally can't do anything else. Which one would you guys prefer to do? What was that? All right, so the suggestion is to do mesh analysis. I have no problem with that, but I would argue, we'll do mesh analysis, but I would argue that nodal analysis would be the smarter play because it's going to be 3 equations, 3 unknowns either way. So why not just solve for the voltage directly? But we'll do mesh. So I'm going to call this guy up top phasor mesh current I1. I'm going to call this guy right here phasor mesh current I2. And this guy phasor mesh current I3. Give me just a second to look at this terrifyingly cluttered desktop and make sure I have MathCAD installed on this computer, and it looks like I do. Great. All right, so we have an interior current source, right? So the current source is not on the perimeter of the circuit, it's on the inside of the circuit. So what does that mean? I'm going to have to write a super mesh KVL equation, okay? So I'm going to define my super mesh in green, and it's going to be this path because that's the smallest possible combination of meshes that encloses my current source. All right, so because I have a current source, I'm going to have a current relationship equation. What is that going to be? I2 minus I3 is equal to 25 angle negative 90 degrees amps, okay? Now we would do our Kirchhoff's voltage law equation around our super mesh. Holy stromboli, my penmanship got terrible there for a second. This would be super mesh 2, 3. Kinsley, I'm going to pick on you because I know your name. How am I going to do this super mesh? Bottom left-hand corner, so right around here. It would be J2 ohms, right? I got to do the whole impedance. Yep, J2 ohms. All right. That is absolutely correct. All right, then our last equation is going to come from mesh 1. Noah Perkins, you made the fault of telling me your name, so I'm going to pick on you now. How am I going to do KVL around mesh 1? Yes. Equal to 0. Wonderful. All right. Like I said, you guys pretty much know how to do a nodal and mesh analysis pretty well because that's what you've been relying on to do everything to this point. So I have these three equations, these three unknowns. Let me open up MathCAD and get my keyboard. All right, so I am going to have to set up a solve block. I'm looking for my three different mesh currents, I1. I'm going to say just arbitrarily that it's going to be 1. Oh, that's not what I wanted. Angle, by the way, the hotkey for angle is Control-Shift-P. 0. And there is no hotkey for the degree symbol, so I'm going to be lazy and type in degrees. And it's going to have units of amperes. And I'm going to do the same guess values for I2. And over here, I'll do one for I3. Let's see if that was a sneeze. Not sure what happened there. All right, so our first equation, if I recall correctly, was I2 minus I3 is equal, so control equals because I'm doing a constraint equation, and it was 25 angle minus 90 degrees. Is that correct? My second equation, gosh, let's see, that was J2, which I can put this in MathCAD as either 2i or 2j. Either way works perfectly fine, but if I do J2 by itself, it will freak out. So put the same as when you're using your calculators, put the imaginary operator after the number. This is ohms multiplied by I2. Plus minus 1j ohms multiplied by I2 minus I1. oops, plus 1 ohm multiplied by I3 minus I1 is equal to 0. Is that correct? You guys have the, hopefully, equations in front of you. I don't. Alrighty, and then lastly, around mesh 1, we had 1 ohm multiplied by I1 plus 1 ohm multiplied by I1 minus I3 plus minus 1J ohms multiplied by I1 minus I2. I want to point something out here for those of you who haven't used MathCAD a lot. It's really easy to make it give you some errors in here because of the amount of parentheses and stuff like that that we're using. So I'm not 100% sure, but we can find out momentarily. But what I've done here is I've explicitly multiplied, anytime I had the imaginary operator, I explicitly multiply that by a unit of ohm. And anytime I am multiplying my impedance by some combination of currents, I am also explicitly multiplying. So I'm not just typing the next thing in, I'm hitting the multiplication key and then doing it. Because sometimes when MathCAD sees things in parentheses, it treats it as a function of whatever is outside the parentheses. And that will cause this to go horribly awry. So if we remember to explicitly multiply every time we are multiplying things, it'll take care of that and we shouldn't get any errors. All right, so now what I'm going to do here is I'm going to drop in a matrix. You don't necessarily have to do this step. I'll explain why I do it momentarily. So I'm going to put I1, I2, and I3 here. Find I1, I2, and I3, and hit equals. And I get 3 currents all in rectangular form. Nothing remotely wrong with that, but it's not my personal preference. So for those of you who like to play around with MathCAD to help with your homework, if you go to the Math Formatting tab here, and you go to this bottom right-hand button in this window, you can tell it to express your answer in rectangular form with I as your imaginary operator, rectangular form with J as your imaginary operator, polar form expressed in pi radians, polar form expressed in radians, or polar form with the angle expressed in degrees, which is the one that I prefer. So I literally just press that button and it converts everything to that format that I like. Okay, so
For the omega, you click on the symbol omega, does it just know that you're talking about resistance?
So how I got those omegas, if I type capital W and Control G, that converts the W to its Greek counterpart, which is omega. Now, your question was, is it going to interpret that omega symbol as a unit of 1 ohm? And the answer is yes. And we can tell if it didn't, it wouldn't give me the unit here of amperes. It would have some weird mixed thing, right? So, all right. So we have our 3 mesh currents. Now what would we need to do to find that voltage V1 double prime? Let's look back at our circuit schematic diagram. What is V1 going to be? Okay, so V1 double prime should be negative I1 times 1 ohm. All right. Anybody disagree with that sentiment? No, just good old Ohm's law. Now, obviously, this isn't going to take a whole lot of computational effort here. Meaning I could simply take my value of I1, which is told to me as 11.785 angle 135 degrees, and then multiply that by a factor of -1, which would mean I would just add or subtract 180 degrees. But I want to show you something regarding MathCAD. So the reason why I chose to put a matrix right here is because that matrix is my way of telling MathCAD to store these results so that I can reference them outside of this solve block. So if I type in V1 is going to be, let's see, negative I1 multiplied by 1 ohm and hit equal, it gives me the answer in polar form, which I don't like. So I can switch it and we can see it's got the exact same magnitude and it subtracted 180 degrees from it. Nothing wild or crazy there. But if I didn't have that matrix, it gives me an error. And it's giving me that error because it didn't store any of that information, right? So this is a short and quick, quick and easy way to make sure that everything that you need is saved. Tap on those, somebody go outside and tell those people to come in. That's fine. We're going to work another problem and then we got the lab, so nobody's really missed anything. All right, so now that we have those two values for V1, 11.785 angle 45 degrees, let me find that. (11.785 angle negative 45 degrees volts, if I'm not mistaken. That's correct. How do I go about tying everything together and finishing solving this problem? So, for those of you that have just joined us, we've been working a problem for a little bit, and we've employed the technique of superposition to try to determine what the voltage drop over this 1 ohm resistor here is. And we've been working the circuit in the frequency domain. We first did it with the voltage source on and the current source off. And we're able to use voltage division to get a particular voltage. Then we did it with the current source on, voltage source off, had to wind up using mesh analysis to get our particular voltage. So what is our next step? Anybody? Right, so V1 with both sources on is simply the combination of V1 with the voltage source on and current source off, and V1 with the current source on and voltage source off. So that's going to be 5 angle 90 degrees volts plus 11.785 angle, gosh, my penmanship went nuts there. (45 degrees volts). So I can simply just add those numbers together. So 5 angle 90 plus 11.785 angle minus 45 is 8.975 with an angle of negative 21.801 degrees volts. And now the $1 million question, which I've actually been forgetting to do. How do I convert that answer back to the time domain? Sure, that literally you couldn't put it better. So to get our phasor representation, we took, say, the magnitude of this guy, 15, and the phase angle of 0, and that gave us our frequency domain representation. To go back, we simply do the other thing. We take the magnitude of our complex number, put it into our time domain expression. So that would be 8.975 cosine omega, which was 10 to the 3 t, and now we put in our phase angle, negative 21.801 degrees volts. So converting from the frequency domain to the time domain and vice versa is a very, very straightforward process. All right, let's work another problem. I'm going to pick on some of the other people that came in. So you guys that have been here, get a breather. All right, let's see. I'm going to call this guy I1 of t. This guy down here will be I2 of t. Millihenries, 250 microfarad, 73 ohms. Call this guy ES of t. This is a 10 ohm resistor. We're trying to find this current I of t, where let's say that I1 of t is equal to 40 cosine 10 to the 3t minus 45 degrees amps. I2 will be 60 cosine 10 to the 3t. Sorry, let's make that milliamps. Milliamps. And lastly, Vs of t is 5 cosine 10 to the 3t plus 17 degrees volts. So we have this time domain circuit, and we are going to, again, work it in the frequency domain to avoid the terrifying amount of calculus and trig functions, and try to get the time domain current I of t that is leaving our voltage source. So your name is Jonah Fitzgerald, correct? Mr. Fitzgerald, what should I do first? Exactly right. Convert everything to the phasor domain equivalent. So let's redraw this circuit real quick. This current source was directed to the left. Alrighty, so let's start with converting our currents into the frequency domain. Let's see. Ms. Pereira, can you tell me what the phasor representation of current I1 is going to be? I'm sorry, what was that? Yes, the phasor representation of current I1. No problem. All right. So to convert from the time domain to the frequency domain, we simply take our magnitude, which is 40, and our phase angle, which is minus 45 degrees. And that is literally it. As long as we are given cosine functions, that's all we need to do. If we're given a sine function, we convert the sine to a cosine and then follow the exact same steps. So with that in mind, I'll give you another stab at current I2. 60 angle 0 degrees. Wonderful. Just like that, she knew what to do. All right, lastly, we have our phasor domain representation for our voltage Vs. Mr. Anders? I can't remember if it's Anders or Amerson. You're Anders? Okay. What's the voltage going to be? That is correct. So I'm just going to put these guys on my schematic diagram. Let's see. All right, so now we're going to have to deal with our impedances, okay? So, oh gosh. Ms. Dugas, do you remember what the impedance of a resistor is? Exactly right. The resistor value just stays the same. So this 73 ohm resistor will continue to be a 73 ohm resistor, and this 10 ohm resistor will continue to be a 10 ohm resistor. I apologize for not remembering to include my current of interest I. All right, so gosh, I'm running out of Colton. I remember your name. What am I going to do about my capacitor? Yes, so we are going to determine the impedance of our capacitor, which is defined as 1 over j omega c. Absolutely right. So that's going to be the same as negative j divided by omega c, where omega in this case is what? It's known. So omega is the bit that gets multiplied by t in our sinusoidal function. So in this case, that would be 10 to the 3. C was 250 times 10 to the minus 6. And I can't do that in my head. I think it's going to be J40, but I'm not 100% sure on that. So let's see. 1 over 1 times 10 to the positive 3 times 250 times 10 to the minus 6. Dang, J4. So minus J4. So we're going to have minus J4 up here. And I'm running out of people whose names I remember that just walked in. So somebody else tell me what I'm supposed to do with my impedance. Correct. Where L was 13 millihenries. Or, oh, what the heck did I just do? It looks like I've rotated this. How do I unrotate it? All right. Plug in the keyboard. Or actually, I bet I can just hit edit, undo. There we go. All right. 13 times 10 to the minus 3. So this one's going to be pretty easy. It should just be J 13 ohms, right? So what should my next step be? I've completely converted my circuit from the time domain to the frequency domain. So this is our choose your own adventure time of how we're going to approach analyzing this circuit. And there are a couple of different ways that I can think about doing it right now. Anybody have any ideas? All right, nobody's saying anything, so I will tell you what's screaming at me. I can observe that I have a practical current source right there, and another practical current source right here. So I would argue that if I do source transformations on both of those practical current sources, this will become a single loop circuit, which will be trivial to analyze. Anybody disagree with that? The other thing that was jumping out at me would, let's see what's going on in chat. Source transformations. Thank you, Kay. That's absolutely correct. So the other thing that was jumping out at me was, again, trying to use superposition. And the reason why superposition would make things pretty simple, and let me think if it will make things even more simple. So just thinking out loud here, with my voltage source on and both of these current sources off, I have a single loop circuit and I can figure out the current that's leaving that voltage source pretty easily, or the voltage source's contribution to that current pretty easily, right? If the 60 milliamp current source is on, then it's simple current division. So one thing that it may not be intuitively obvious to all you guys, but because the bottom of this guy is connected to ground, the bottom of this guy is connected to ground, and the bottom of this guy is connected to ground, we can think of these as connected like this. So this is all just one big node here at the bottom. So that's why if I turn off this current source, I can just use current division. And if I turn, if I turn on this current source here and turn this guy off and short circuit this guy, current division will give me an answer. And again, the exact same thing with this guy on, this guy off, and this guy off. I again have a way that I can just do current division. But I think the source transformation route is going to wind up being the least amount of work. So that's the way that we're going to go. So always lots of different ways that we could do this. Obviously, also we could do nodal and mesh and all that kind of jazz if we were so inclined, but I am not inclined. All right, so crash course on source transformations for those of you that maybe don't remember what's going on. When I have a current source IS in parallel with a generic impedance ZS, like so, I can convert that to an electrically equivalent practical voltage source. Where the impedance ZS stays the same and my new voltage source is simply IS times ZS. And I would like you guys to notice that the head of the arrow corresponds to the positive polarity terminal of the voltage source. If, and we're not going to do it on this particular problem, but if I wanted to go the other way, meaning I had a practical voltage source that I wanted to convert to a practical current source, that does not remotely look like a V. The rules for that are my impedance ZS stays the same, and this current will be my voltage divided by my impedance ZS. All right, so with those relationships in mind, my circuit should look something like this now. Let's see, that was a resistor, so it's going to stay a resistor. That was my 73 ohm resistor. Then I'm going to have a voltage source, positive polarity terminal on the left, because the head of that arrow was on the left, in series with my capacitor, whose impedance I don't remember off the top of my head, so we'll get that in a second. In series with my inductor, in series with a resistor, in series with my 5 angle 17 degrees voltage source. So this resistor, still 10 ohms. This is the phasor current I I'm looking for. All right, so what was the impedance of my capacitor? Because I've forgotten, I'm too lazy to scroll up. I think that was my inductor. Negative J4 there, J13 there. All right, so this guy is going to have a value of 40 angle minus 45 degrees milliamps multiplied by 73 ohms. So 0.04 times 73 gives me 2.92 with an angle of minus 45 degrees volts. This guy is going to be 60 angle 0 degrees milliamps times minus J4 ohms. So 0.06 times 4 is 2.4. Well, because I'm multiplying by minus J, that's the same as negative 90 degrees volts. All right, so anybody have any questions, comments, or concerns about how I've applied source transformations to convert this into a single loop circuit? And both of those grounds represent the same node, or how I got the numbers that I got. All right, so how am I going to solve this thing? Combine all the impedances. Okay, so I would argue that we can combine all of the impedances, and we can also combine all of the voltage sources. So this guy is going to look like, I'm putting my impedance on the left-hand side, and I'm going to put my voltage on the right-hand side, and I'm looking for this current, I. So with regards to my impedance, let's see, it's going to be, I'm just going to add all the real parts together. So 73 plus 10 looks like 83. Minus J4 plus positive J13 looks like plus J9 ohms. So that's my equivalent impedance for everything because it's all in series. So I just add the real parts together, add the imaginary parts together, and I'm good to go. So anybody have any problem with my equivalent impedance? All right, for my equivalent voltage source, let's see. So as I follow this current I around, I can see that the 5 angle 17 degrees volts source has the same polarity as the 2.4 angle negative 90 degrees volt source, and it has the opposite polarity of the 2.92 angle minus 45 degrees source. Anybody not seeing what I'm seeing? So I'm just following the current along its path. I see the negative sign first for the 5 angle 17 and the negative sign first for the 2.4 angle minus 90. So they have the same polarity. I see the positive sign first for the other one. So it has the opposite polarity. So what am I going to add together to get my final equivalent voltage? Yes, I am adding the voltage sources together, but how am I going to do it? What? That is exactly correct. So my equivalent voltage, let's just call it VEQ phasor, will be 5 angle 17 degrees volts plus 2.4 angle minus 90 degrees volts minus 2.92 angle negative 45 degrees volts. And all of those together combine to be 3.166 with an angle of positive 14.132 degrees volts. Any questions on how we combined all of those voltage sources? We're revisiting some very old techniques in this class, like source combinations here, I think was lecture 4. So it's been a hot minute since we've done it. So if you need a refresher, I'm happy to explain why we're doing what we're doing. All right, nobody seems to be asking any questions. So our last step then, how do we determine that current I? Just Ohm's law, absolutely right. So our current I is just our equivalent voltage VEQ divided by our equivalent impedance ZEQ. So that is going to be 3.166 angle 14.132 degrees volts divided by our impedance of 83 plus J9 ohms. Which I get to be 37.924 with an angle of 7.944. Or milliamps, or in rectangular form, 37.560 plus J 5.241. Milliamps. All right. So we have worked several steady state sinusoidal circuit analysis problems. There are several more available for you to look at on the old tests and all that kind of good stuff. So what's going to happen on Friday, there's an electrical engineering industrial advisory board meeting that I will be stuck at literally all day. So Dr. Harbour is going to come in and he's going to start talking about our power relationships when we're dealing with steady state sinusoidal circuits. The first day's worth of material isn't that bad. The second day's worth of material is considerably more ugly. So I'll be here on Monday to torture you with more complex numbers, to put it arguably politely. All right, so we got 20 minutes left, and we do technically have a lab to do today. For those of you that don't have the sheet, come grab one, and let's knock this out while I make sure that I uploaded it to Moodle for those of you that are doing things online.
Listen to my calculator for next week.
Should I do 2.92 or 2.42? That might be the issue. I did 2.42, not 2.92.
Oh, that's a 4. Okay.
That was supposed to be a 9. I made a mistake. You got it right.
Thank you.
All right, so just to be really clear here, there is a slight error because I did something dumb. So this is 2.92. I typed into my calculator 2.42. So this equivalent voltage is slightly wrong, which means that this current is wrong. The methodology is right. I just put the wrong number in my calculator. We were running out of time. I'm moving forward. All right, let's see if I uploaded this mini lab. All right, looks like I did. Great. Let me open up the waveforms thing, which will be way easier if I just type in waveforms instead of looking over all that crap. All right, detect the device now. Yes. All right, so let's see what is what with, here's what I'm looking for. All right, connect the Explorer board, did it. Open waveforms, did it. Circuit's already set up and all that kind of jazz. It looks like, all right, so using a multimeter, we're gonna measure our 100 ohm resistor. Pulling it off the table.
Dr. Harvin, I'm not seeing the lab sheet on Moodle.
You're not seeing it on Zoom or on Moodle?
I thought you said you uploaded it to Moodle.
Yes, if you go onto our courses webpage, and then you click on the thing that says mini labs, and then you scroll down to
Oh,
number
it's on
7.
it's on the other, it's not on the combined. Okay.
Right, it's on
Okay.
all. Yep.
All right. Thank you.
All right. 101.8 ohms. I can't draw on this, so 101.8. And now I gotta remember where this guy was wired up, and I believe it was from here. Here, we'll find out whether I broke the circuit in a minute. All right, build the circuit on the Explorer board. It is literally a very, very simple and trivial RL circuit. So I have my analog wave generator connected to one leg of my resistor. The other leg of my resistor is connected to my inductor. The other leg of my inductor is connected to ground. I have scope 1 measuring the voltage drop over my inductor. Scope 2 is measuring the input signal directly. All right, all that looks groovy. Blah, blah, blah. Connect things. I did it correctly. All right, so click the run button on the oscilloscope and run AWG1. So let's open up lab 7. Board power is off. Let's make this go. I wish I could make that thing go away. Wave gen, scope. Let's look at our scope. All righty. So here is our signals, okay? The yellow curve is the voltage drop over our inductor, if I'm not mistaken. Yes. And the green curve is representative of the current in the inductor. So we are asked from the graph, does current lead or lag the voltage across the inductor? So if we look at two peaks which are close together, is the yellow curve first in time or second in time? It's first, right? So the yellow hits its peak and then the green hits its peak. So the yellow is the voltage, the green is the current. So we could say that the voltage leads the current or the current lags the voltage. All right, in an inductor, the current should always lag the voltage. And let me explain why that is real quick. So our relationship in an inductor is V is equal to j omega L times I, which is Vm e to the j theta V is equal to omega L Im e to the j theta I, and if we multiply it by j, that's another e to the j 90 degrees, which means we'll have omega L Im e to the j theta I plus 90 degrees, which means theta V is equal to theta I plus 90. So our current should always lag our voltage by exactly 90 degrees. All right, let's pop back over here. So if we change the frequency to 50 kilohertz, and we look at our signal, how does it affect the output? Okay, so the position of leading and lagging will not change ever in an inductor, all right? What does changing the frequency or increasing the frequency specifically do to the impedance? What's the equation for the impedance of Kirk? Okay, j omega L. So if omega increases, what happens to Z? It increases. All right. So we have increased the frequency from 17.5 kilohertz to 50 kilohertz, which means we have increased the impedance of our inductor. What happens when we increase the impedance of something? It's the same as increasing the resistance, right? So we should have observed that in our simple voltage divider circuit, because that's exactly what we have, it's a voltage divider circuit where we're using a resistor as one element and the inductor as the other. When we increase the impedance, the voltage drop over the inductor should go up and the current flowing through the inductor should go down because it's just the same as if we didn't increase the resistance, right? If we change the frequency to 5 kilohertz, we still see that our voltage leads our current, because again, that will literally never change, but obviously lowering the frequency causes the impedance of the inductor to decrease, which means we should see that the voltage drop goes down and the current goes up. Does that make sense to everybody? All right. That's how we can actually use inductors and things like that to form filters, right? So at very, very low frequencies, inductors behave like a short circuit. What happens at very, very high frequencies? So as omega approaches infinity, what does the impedance of an inductor become? Infinite. So at low frequencies, an inductor looks like a short circuit. At high frequencies, an inductor looks like an open circuit. So that's how we get a high pass filter response, which is beyond the scope of this course, but I find it interesting. All right, so we're on to page 4 here. It tells us to change the frequency of AWG1 back to 17.5 kilohertz. So go to here. You're gonna have to type. And it tells us to adjust the horizontal cursors X1 and X2 to find the time phase shift. So I'm going to place cursor 1, if I can grab it there, on the peak of our voltage signal, and I'm going to place cursor 2 on the peak of our current signal. And it tells us that our time shift, X2 delta 1, is 14.772 microseconds. So delta T is 14.772 microseconds. So somebody do the math and tell me what that corresponds to with regards to an angle in radians and an angle in degrees. And the math that you need to do is literally defined on the sheet. Yes. So you should have 2 pi times 17,500 times 14.772 times 10 to the minus 6 seconds, and give me a number. And that number will be the angle, the phase angle between those two signals in radians. You've messed up something somewhere. It should be just 1.624. Yeah. All right, so 1.624. If we multiply that quantity by 180 and divide by pi, so 180 over pi, that's simply converting our answer from radians to degrees. And I get 93.0636. So it's not quite 90 degrees, but it's pretty darn close. Anybody have any idea why the answer isn't exactly 90 degrees? So our inductor is not an ideal inductor. It's formed by a piece of wire that has a finite resistance. And so that finite resistance in series with the resistance of the resistor itself is throwing that off a little bit. That's all it is. All right. Now we need to replace our inductor with the capacitor. And we're, let's see, blah, 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 change the frequency to 25 kilohertz. Let me see what's popping in chat. Okay, okay. Legend. All right. From the graph, does the current, which is the green curve, lead or lag the voltage? So which occurs earlier in time? The green, which is the current. So for the capacitor circuit, the current is leading the voltage. If we increase our frequency to 50 kilohertz, what's happening to the impedance of our capacitor? So an increase in the frequency does what to the impedance of a capacitor? It decreases it, right? Because our relationship is 1 divided by j omega L. So impedance is inversely proportional to frequency in a capacitor. So, excuse me, as we increased our frequency, we lowered the impedance of the capacitor, which means we should see that the voltage drop got smaller. So the voltage drop over the capacitor got smaller and the current flowing through the capacitor got larger. If we drop our signal frequency down to 5 kilohertz, now we see that the current value is very small, or the magnitude of the current is very small in comparison to the voltage. The voltage increased, and it's because we have increased our impedance. So put it back to 25 kilohertz. And we're going to do the same thing. I'm going to put marker 1 on my voltage. Just so we're consistent. Marker 2 on the positive peak of my current. And so I have a change in time, or a time shift, of negative 9.7302 microseconds. So delta t is negative 9.7302. Take a moment, calculate what that corresponds to with regards to a phase angle in radians, and then degrees. Negative 1.528. All right. When we multiply that by 180 divided by pi, we get negative 87.518. So still, but yeah, I got negative 87.5718. That's correct. So it's not quite negative 90 degrees, which is what would be expected, but it's pretty dang close. And that is the lab. Alrighty. Like I said, Dr. Harbour will be with you guys on Friday. So I will see you guys all on Monday. No. I will be in a meeting from 8 a.m. until roughly 3:30 p.m. I'm out.